So here's what I want you to do. This next property is one you're very familiar with. Again, since first grade, second grade, and it's one we've already put on our list, state. Does anybody know what it means when a scientist says what state something is? And they say, what state is this in? What do they mean by that? What do they want to know? Price it.
In the form of being a solid, liquid, or gas.
Yes, so, and for our purposes in science, one of the things that we talk about when we say state at. Yes, because we know that any material, we can make it change its state. Okay? What do we need to do to make something change its state? What do we need to do to the material to make it change its state? Here.
Either add heat or cold.
Well, yeah, so we don't add cold, we either add heat or remove heat. A lot of times we think of it that way, oh, let's give it some cold. But actually, cold is really a measure of less heat than you had before. So in order to make something change state, we need to either add heat or remove heat. For example, I've got this water here. Right now, what state is this water at? We're at room temperature. Liquid. Water state at room temperature is a liquid. What would I need to do to this water if I wanted to change it from a liquid to a solid? Brady. Yeah, I need to remove some heat from it. What if I want to take it from a liquid and turn it to a gas? What would I need to do then? If I wanted to take it from a liquid, turn it to a gas. Eli? Yes, add heat. So any material, we can get it to change states by either adding or removing heat. Now, here's my question for you. You've been learning about solids, liquids, and gases since you were little. Okay? I held up that water and said, what state is this in? Immediately, everybody said, liquid. How did you know it was a liquid? When you see a liquid, how do you know it's a liquid? What is it about liquids that helps you identify them? This piece of paper, this card, what state is it? It's a solid. How did you know it's a solid? What is it about this that makes your brain say, oh, that's a solid, but that's a liquid? And when you see a gas, how do you know it's a gas? Hands down for a second. Since I'm starting this little mini unit on solids, liquids, and gases, the three states that we're most familiar with. Now, there's a fourth state. Have you heard of the fourth state, plasma?
Yeah.
So there is a fourth state, plasma. We'll talk about it briefly, but right now at this level, they're mostly going to talk about solids, liquids, and gases. We'll come back to plasma, though. I do want you to know about it. You won't be asked that on GCAP. So here's what I want you to write down. I'm starting this out about solids, liquids, and gases. I want to know how much you understand about them. And you're not with me, you guys. Write down for me on that paper, how do you know the difference between solid, liquid, and gas? What is it about solids that they have that helps you say, oh, that's a solid? And what do liquids have that when you see them, don't write yet, how do you know it's a liquid? And then how do you know it's a gas? So what is it about each of the three that helps you tell the difference between them is what I'm asking. Question, Cam? No, I'm not scoring you on this. This is information for me because I just want to know what your understanding is so far about solids, liquids, and gases. All right, I'm going to give you about 5 minutes, so write as much as you can. Don't worry if you're not for sure, just write what you can, okay? Tell me, how do you know a solid when you see it? What is it about solids that help you identify them, to know if it's a solid? What's one thing you look for, Tyler? What do you mean nothing can go through it?
Like a rock, like you can like drill a hole in it.
Okay, so like if you try to touch a solid, you can't just push your finger through it. Is that what you mean? Okay. Why is it you can't just push your finger through solids? Like here's a solid wall. Why can't I just push my finger through it? Mallory.
It's like held together, it's hard.
Yes, it is held together, is it? Now, some solids are harder than others, right? Cheese versus a wall. You know, if I have a piece of cheese, but just by touching the cheese, I don't go through it, do I? I have to put some force behind it to go through it. Could we go through this wall?
No.
Not with my finger, but is it possible to get through this wall?
Yes.
Yeah, what could I use?
A
The drill, yes. So it's not so much that you can't get through them because they are held together tightly, Mallory said. Do you agree with what Mallory said, that they're held together? They're held together, and so you have to put some force to get through them. Compared to water, do you have to use a lot of force to put your finger through water? No. So as far as being held together, what does that tell you about the way solids are versus how liquids are? Landry?
Liquids are very loose.
Yeah, so liquids must not be held together as tightly. What else? How else do you know it's a solid? The part, you can, when you touch it, you don't automatically go through it. Cameron?
Shape and movement.
What do you, he said the shape isn't moving. What do you mean by that, Cameron? The shape isn't moving. You're on to something.
If you had a shape, like if it wasn't moving, then it'd be a leak. Like this.
You're on to something. He's on to something. He said the shape isn't moving. Ryan, add to what he said.
It'll stay the same shape.
Yeah, it has a shape of its own, doesn't it? Do liquids have a shape of their own? No. And a lot of you wrote down about liquids' shape. A lot of you wrote down that liquids take the shape of the container that they're in. Right now, McKaylee's water, which is a liquid, is in the shape of this bottle that's holding it. If I pour out her water on the desk, aside from her being angry with me like she's doing, is it going to stay in this shape when I pour it out? No. So there's something about a liquid that keeps it from keeping its shape that solids have. If I have a solid, if I put this solid right here and put it in that bowl, does it change to be a bowl shape? No, it keeps its shape. So Cameron's right. Solids have a shape of their own, and they don't change the shape unless we do something to change it. Now, could I change the shape of McKaylee's pencil? Yeah, what would I need? What can I do to change its shape? I could break it. What else could I do?
You could use a torch.
Yeah, I can use a torch. That'd be violent, but yeah. I can, melt it. So solids have a shape, and they keep that shape unless we do something to interfere with that, okay? Now, so you mentioned the solids. You can touch them, and you don't automatically go through them. You have to have some force. They have their own shape. Did anybody put anything else about solids that we've not mentioned? What about liquids? How do you know something's a liquid when you see it? So how do you know something's a liquid? McKaylee?
A liquid isn't like hard like water.
Okay, so when you touch a liquid, what does your hand do? When you touch a liquid, what happens? Yeah, easily, yeah. You don't even have to really put in force. As soon as you touch it, it moves out of the way for you, right? What else about liquids? What else? How else do you know if it's a liquid? So you know if you touch it, your hand goes right through it. Jalen?
It's wet.
Yeah, so it's wet. What else? Nia?
The thing that helps me identify a liquid is that it moves easily and it can fit inside almost anything.
So you mentioned two things. Let's talk about that moves easily. What do you mean by that? It moves easily.
That if you just take your hose and you click it, it'll move.
Yes, and in science we describe that it flows. Do you know what that means, flows?
Yeah.
Water will flow. You can pour it through a pipe and it'll go through the pipe. Remember, that's how we heat and cool our building. We have water that flows through these pipes. We heat the water up and run hot water through the pipes, and then that heats the air that we force out, the vents. And then in the sun, when it's warm weather, we have a chiller that cools off the water, and we run cold water through the pipes. Liquids will flow, okay, because they move easily. And what was the second thing you said, Nia?
It can fit in almost any container.
Why is it that liquids can fit in almost any container? Why is it? Why do liquids, what do you know about liquids that allows them to fit in almost any container? Landry?
They don't have a shape.
They don't have their own shape, do they?
Actually.
Yeah. whatever container they're in, they take that shape. I just mentioned that. We take Michaela's bottle and pour it out. It's not going to be in the shape of the bottle. It's lay there on its side. What's it going to do?
It's going to spread out.
It's going to spread out. And so something about what liquids, and I know we're using water as our example a lot, but remember this is any liquid. They don't have their own shape. Anything else about liquids help you identify them? We said they're wet, they flow, you can put your hand through them easily, they don't have their own shape. Now, here's the hardest one, gases. When something's a gas, you say, oh, that's a gas. How do you know it's a gas? What is it about gases to help you identify them? Tell your neighbor first, because some of you are not talking to me at all. I'm getting worried. Back with me, how do you know? This one's the harder one, I think. How do you know something is a gas? What helps you identify? Oh, that's a gas. Eli. Well, now, let's talk about that. A lot of people put that down, that you can't see a gas. Do you have anything to argue against that? You can't see a gas. The other day, we were looking at a video clip, and I said, oh, most gases you can't see, but does anybody remember? Tyler.
The gas off of Mercury, I'm going to see it.
No, normally you can't, because remember we had to do that special light, that UV light. Yeah, we had to use that special light to be able to see it. But I had a really good example. Brady, do you remember? Chlorine gas. You remember when we did the chlorine? We saw the sodium metal being heated up. What color was chlorine gas? A greenish yellow, yes. Now, it was concentrated in that small container. If they had opened that container, the chlorine gas would have spread out in the whole area, and you would not have noticed it because it spreads out. So don't say, oh, if we can't see it, it's a gas. Some gases do have a color. Chlorine's an example of it. Okay? So what else? Most gases, though, we can't see them. They're colorless. What else about gases?
Gases are sort of similar to liquids in this way. Like, they take up the space like a liquid does.
What do you mean by that?
And, like, an area, like this room, like air is filling up this room.
So you're getting close to another thing that liquids don't have. Let me go to the first thing you said. She's talking about the shape. Do liquids have a shape of their own? No, they take the shape of whatever they're in. What about gases? Do they have their own shape? You ever seen a triangle of gas floating around? No. Think about when you put a gas into something you've all probably done, inflated a balloon.
Yeah.
That's now, listen, time out on that. A lot of kids think that, so we call gasoline gas. But if you've seen gasoline, is it a liquid or a gas? It's a liquid. I don't know whose decision that was to call it gasoline. That's confused kids forever. Yeah, so gasoline is a liquid, okay? But we're talking about the state, a gas. You've blown up a balloon. Does the air that comes out of your lungs have its own shape? No. What shape does the gas end up being? Whatever if you put the gas, you blow up a long skinny balloon, it's going to be that shape. If you do the round one, it'll be that shape. When you've seen someone inflate a tire before, does the gas have its own shape and change the shape of the tire? No. So gases, like liquids, don't have their own shape. Anything else about gases? Yeah.
I had identified a gas by observing it, but like.
Okay. Now, some gases do, but some gases don't. Now, we already know what causes things to float. What causes things to float?
Air.
Well, what causes things to be buoyant, though? We just study this. What made some things float and some things sink? McKenna? Density, yes. So if the gas is less dense and the rest of the air is in, it'll float. Okay. Let me ask you this. I want to go back to what McKaylee said. She said if the gases in this room are filled up, they filled up the whole room. What do you think about what she said? Let's suppose that we have somebody come in here and they take a pipe and they pump air into here. Let's say they just pump some pure oxygen into this room. Would the oxygen just collect over in the corner?
No.
What does it do?
Spreads out.
Yes, it spreads out. So one of the properties a gas has is that it spreads out to fill up whatever container it's in. If you put it in a small container, as soon as the gas gets in there, it fills up that whole container. Remember that thing of chlorine? The chlorine wasn't settled at the bottom, was it? No, it's spread out to fill out its own container. Okay, and so that's why when we see gas, things, if we can contain the gas in a balloon, it'll float up higher. But if you just pump the helium out, the helium doesn't just automatically, it starts spreading out everywhere. So gases, whatever container they're in, they spread out to that whole container. When you blow up a balloon, does the air just collect in the bottom of the balloon and go rise up? No, it spreads out and then stretches the balloon out. Same thing for the tire. Does the air collect in the bottom of the tire and then fill up like a liquid? No. So one of the things gases do is they spread out to fill their container. So what we're going to use to look at why solids, liquids, and gases have these different properties is a model from this website here. And remember, we talked a little bit about models already, about how, remember we talked about atoms, how we have models of atoms. Why do we use models to help us understand atoms? Yes, in the case of an atom, they're so small, we can't really see them. No one's ever directly looked at an atom. So a model helps us to understand how it looks. So we're going to do the same thing here. One of the biggest reasons that solids, liquids, and gases have the properties that they do is at their particles. Now, we know that all matter is made up of tiny particles. What are those particles called? Atoms, yes. And then the atoms, when it's different elements, they join together and make a compound. So we're talking about the smallest piece of the compound here, molecules. And so what we're going to do is look at the particles of solids, liquids, and gases. Now, notice how we've got this beaker here, and there's something in it. Can you tell whether it's a solid, liquid, or gas? What is it? A solid. How do you know it's a solid? What tipped you off that this is a solid in this beaker? Yes, it's held together. What else? Braided. It has its own shape, doesn't it? So right away, if I see something that's got its own held together with its own shape, I know it's a solid. So the way this website works is I'm going to click on solid, and then what it's going to do is going to show us how the particles in a solid look. Now, I don't know what this particular solid is supposed to be. It looks like an amethyst to me. And what they're going to do, you can see in this big round circle, they're pretending like this is some sort of microscope that lets you see how the particles are behaving. What I want you to do is look at the particles in the solid and tell me what you notice about them. There are 2 or 3 things you'll notice right away. So I'm going to click on solid. Tell me one thing you notice about how the particles are. So we're looking at the molecules of this solid. What do you notice, McKenna? Yeah, they're all packed in pretty tightly, aren't they? They're squeezed in there. There's not much space in between them, is there? What else do you notice, Neela? Yeah, they're moving. They are moving. Can you see how they're moving a little bit? Now, let me ask you this. Are they moving all around? No, they're sort of like shaking or vibrating in place, aren't they? But they are moving. Anything else you notice about them? Mallory? Yeah, there are. They're packed in there so tightly, they're squeezed in. What about how they're arranged, how the particles are laid out? What about how they're laid out, Tyler?
They're in nice, neat rows.
They are in nice, neat rows, yes. And if you look right here, you can see they're in a pattern, aren't they? One of the things about a solid is that the particles of it are locked together in a fixed pattern. Now, the pattern that they're locked in depends on what the solid is made out of, okay? So you can see that they kind of remind me of soldiers. They're like all lined up nice and perfectly, like, how soldiers would line up. So the things we noticed about a solid is that they're packed in tightly. They're moving, but are they moving around? No. And they're in an organized pattern. Now, what I want you to do is, I want you to draw the sample in the beaker. I'm going to walk around and let you see some face from last year, how they did it. You're going to draw the sample in the beaker and then draw this pop out where they're looking in the magnifying. As I'm walking around, you can see, you can have the magnification of it. Now, I'm getting ready to turn this to a liquid. And we're going to look at the particles in a liquid. What do I need to do to this solid to turn it to a liquid? What do I need to do? What do I need to do? Raise hands, please. What do I need to do to get it to turn to a liquid? Cameron. Yes, I need to heat it up. So notice that when I click on liquid here, watch what this temperature gauge does. And you need to look at how the particles of a liquid are different than from a solid. Now, this is sort of a lower budget animation. Either they didn't have a lot of money to spend on it, or, it's an older one. And I think it is pretty old. So there are some limitations to this, but tell me what you notice when I heat this solid up and turn it to liquid. Tell me how the differences are in the particles. So I'm applying heat. So tell me one thing that you notice about the particles of the liquid. Bryson? Yes, before they were just vibrating in place. Now their motion's different. They're sliding all around now. What else do you notice? Brian? They are loose, aren't they? Are they in that pattern anymore? No, pattern's out the window. No more pattern. They're not locked into that formation anymore. What else? That way. So all the particles in a liquid slide around. They're not in any kind of formation. Are they as tight as they were? Now, there's some bigger gaps between them now. They're still packed in pretty tight, but not like they were as a solid. What about their speed? McKaylee? They are moving faster. Okay? So the things we've noticed, no formation, spread out a little bit more. They're moving faster. Okay? And they're sliding all around now. Draw the liquid in the beaker and then draw the pop out for the magnification now. So when we look right here at the way the particles behave in a liquid, one of the things that should start to come to mind is the differences between a solid and liquid. Solids have a shape. Liquids do not have their own shape. Think about how the particles are in a solid versus how they are in a liquid. Can you figure out why liquids don't have a shape but particles do, now that you've seen how the particles are acting? Talk to your neighbor first. Now, we're getting ready to move on to gas. What do I need to do to turn this liquid to a gas? Cam? Yes, I got to give it even more heat. Now, as I give it heat, just looking at the matter, how will I know it's turning to a gas? What will tip me off that it's turning to a gas, Tyler? Yeah, what do you mean going away? Yeah, so as they turn into a gas, remember we talked about gases wanting to spread out to the container? There's no lid on this container. So the particles are going to go where? They're going to go into the air, yes. And we'll see that liquid level go down. Some kids think, oh, they've disappeared. No, they're around. They're just not in that container anymore because remember, gas is spread out. If you don't hold the container with the lid, they're going to go everywhere. So there's another clue that you're going to see too. And we've talked a little bit about this clue. You should also see bubbles. Because as the particles in here change from liquid to gas, some of them will be down at the bottom and you'll see bubbles rising up. That's some of this material's turned to a gas. Let's watch. See the bubbles? And what's that above it? It looks like smoke. What is that? Yes, that's this material changing over to gas. And where's it going? Into the... Yes, and right now we can see it. It still looks purple. But since gas is spread out, it'll spread out so much that we won't even see the purple color anymore. Look at the particles now. What do you notice that's different about the particles now? What's one difference you see? Bryson? Much faster. They're wild, crazy. What'd you say again, Bryson, about particles? Crazy, wow. What else do you notice about the particles now? Ryan? Yeah. Yes, it looks like there's just a few, but they're still there, but they're spread out so much that only a few show up in our viewfinder at a time. And some of them have gone off into they're spread out in the room there. What else? Landry? Yes, really fast. In fact, they are going so fast that they bump into each other and ricochet off of each other and spread out even more. Now, this morning we talked about when we blow air into a balloon, we said the air doesn't collect in the bottom and then build up, it spreads out into the container. This is why the particles in a gas move really fast. They're bumping into each other. They keep spreading out. They spread out more and more and more. And that's why when we draw this, we're not going to need to draw a bunch of particles in there because a lot of them are spread out so much they don't show up in our viewfinder. Okay? Braden, what are you going to add? Yes, there's a lot more space. They're spread out so much. Gases are not very dense at all. Particles are really spread out. So, draw this last one. Make sure you label it gas. Okay, now, go to the next clean page. You'll need an entire page for this. I'm going to have you draw a chart, and what we're going to do is we're going to fill in what we know about solids, liquids, and gases from the chart, and then we'll use that to make our foldable. Okay, so we've got solids, liquids, and gases, and what we're going to do is write down the differences in each of these categories. So I'm going to start with particle arrangement. On the solids, what did we say we noticed about how the particles were arranged in a solid? What was one thing we noticed? Okay, Haley. Yeah, so they were packed in tightly. So let's write that. And we'll mention this again down at the bottom of the chart, because we're going to talk about density. That's what we're talking about, how packed in they are. What about how they were arranged, how they were laid out? Nia? Yes, and that was the pattern for that particular material. Remember, each material has its own sort of pattern. So they were organized, right? And it was in a pattern. So let's put organized pattern. And Miss Ewing said it reminded her of what? Do you remember? Yeah, it reminded me of soldiers. Like they're in formation, they don't break formation. They stay in that pattern unless something interferes with it. Now, what about the particles in a liquid? Are they in an organized pattern? No. Yes, yes, you're right. Yes, so no organized pattern for liquids particles. So it makes sense that solids have a shape, whereas liquids do not, because there's no formation there. The particles go where they want. They just, they move this way, they move that way. And what about gases? Are their particles in an organized pattern? No, they were wild as could be. So again, no organized pattern. For gases. Be thinking about how the particles moved in a solid. You remember? How were they moving in a solid? How are the particles moving in a solid? Ryan, how are they moving? Yeah, were they moving all around? No. Vibrating in place. So they were moving, but they didn't have the freedom to slide all around. How do the particles in a liquid move? How would you describe the way the particles in a liquid move? Yeah, were they shaking in place? No, they were moving. Yeah, all around. So they were sliding. Did you notice how they kind of slid past each other? So in a liquid, the particles move, they slide past each other. And we talked about the speed. What did we notice about the speed of the particles in a liquid? They speed up. Yes, they move faster. So I'm going to put in parentheses that they're faster. Let me get this. And what about the particles in a gas? How did they move? Nila, sorry. Yeah, they were moving. What about their speed? They're fast, they were bouncing off each other, they were really wild. So, stay with me, please. Wild, I mean, they were just everywhere. And they were moving, how would you describe their speed? Fastest, yes. We were just talking about the particles of solids, liquids, and gases, how they're arranged, how the particles move. Now, just in general, the shape of a solid versus the shape of a liquid and a gas. You mentioned this at the beginning. You remembered this from last year. What did you tell me about solids and their shape? And you all wrote it down at the beginning of class. Tyler?
It has its own shape.
Yes, it has its own shape. So I'm going to put solids have a definite shape. Now, this thing cannot be circles. I'm going to try to do something around this. It's crazy. So solids have their own shape. It's defined, and it keeps that shape unless we do something to interfere with it, like heat it up or break it. What about liquids? Do they have their own shape? No. Now, make sure you're keeping up with me. They take the shape of their containers. And gases, do they have their own shape? Now, if I put air into a balloon, and it takes the shape of that balloon, when I let the air out, is it going to stay in that balloon shape? No. It has no definite shape either. The same thing for that one. They take the shape of their container.
Right here on the
Yeah.
Cool.
It says
Now, notice that when we talked about it, no one really mentioned volume. Solids, for example, this glue stick, it's got a volume. It takes up a certain amount of space, right? Yeah. So one thing about solids is they have a certain amount of space that they take up, okay? Remember, our clay had some volume, and we messed with the volume the other day, and we changed it, right? It didn't change on its own. So solids have a certain amount of space that they take up, and that's not going to change unless we do something to it, like heat it up, cool it off, or mess around with its shape and change its volume that way. So solids have a definite volume. We can measure it and it'll stay the same unless we do something to mess with that. What about liquids? They have their own volume and certain volume. So liquids have their own volume. They have a defined volume, a definite volume. What about gases? Do they have their own volume? Do they take up a certain amount of space? If I put some gas in here, and let's say chlorine gas, one that we can see, how much space will it take out? The whole thing. What if I transferred it to a larger container? Would it still stay in this small, skinny amount of space? What will it do?
It would go to the shape of the other container.
Yes, and it's going to spread out. Gases, this is the weird thing about gases. The amount of space they take up is limited to the container. We talked about riding in the car versus the new gym. Remember that example? Gases, whatever container they're in, that's their volume. So gases don't have their own volume. Whatever the container's volume is, how much space it takes up, that's what the gas will do. It'll spread out to fill the entire container. The last thing on our chart is density, and I think somebody already alluded to that. Was it Eva Kaylee at the beginning, talking about them being packed in? Remember, density is a measure of how much matter something has for its size. So if something's really dense, it means the particles are packed in really tight. If it's less dense, the particles are spread out more. What would you say about the particles in a solid, liquid, or gas? Which one do you think is the densest? Which one of the particles squeezed in the tightest? McKenna? Yes, solids are the densest. Now, there's an exception to that. We've already talked about it the other day. So solids are generally the densest state of matter. But there's an exception to that. And we talked about it the other day. Water. There's a reason I put water with an asterisk beside it. The other day when we were talking about how ice floated in water, most materials, when they're in their solid forms, the particles are packed in really tight. They're denser than they are when they're liquid. But water does not follow that rule. We said it was a good thing. If water were denser when it was a solid, what would ice do when it's in the water? It would sink. And what would happen to everything living in the rivers, lakes, and oceans as the water froze?
It would become extinct.
Yes, it would be
They would
crushed.
drown.
Yes, it would throw everything out of whack. So, thankfully, water is less dense when it's a solid. But that's not true for other materials. Almost every other material that I know of is actually densest when it's a solid, and then the particles spread out more when it's a liquid. Now, so let's put liquid as the second densest. But remember, water doesn't follow that. So we're writing ourselves a note that water doesn't follow this rule. But most materials, when they're solid, the particles are packed in tighter. When you melt them, turn them to liquid, they spread out a little more. And then what should we put about gases? How are the particles, the density of gases? Well, we're talking about the density. They do flow because they are the least dense. Nice. Yes. That's why when we boil water, which direction does that gas go? That water that's in gas form,
Up and over.
Yeah, it goes up because it's less dense. That's why those bubbles rise to the top. It's less dense than the liquid it's in. No wonder they go up. They're floating in the water. They're less dense. Remember, if something's less dense, it floats.